Math 3 Lesson Summary Video, Parallelogram Conjectures and Proof. This lesson is a solidify understanding task, which takes concepts developed previously and helps you formalize those ideas. The purpose of this lesson is to prove theorems about the properties of parallelograms that were surfaced in earlier tasks as you explored the rotational symmetry and line symmetry of various types of shapes. Explain how you would locate the center of rotation for the following parallelogram. What convinces you that the point you have located is the center of rotation? Recall from Math 2 that there were two types of symmetry that we dealt with. There was line symmetry and there was rotational symmetry. Line symmetry was when a shape could be reflected over a line and land directly back on itself. Rotational symmetry was when a shape could be rotated about a point and could land directly back on itself in less than 360 degrees. So we are looking for the point where we can rotate this parallelogram and actually have the corners line up. You may recall when we did this in Math 2, some shapes have line symmetry, some shapes have rotational symmetry, some shapes have both, and parallelograms were one of them that we figured out did not have line symmetry, but they did have rotational symmetry. So I can't really fold it and have it lie directly on top of itself, but I should be able to spin it. But in order to do that, I have to find the center of rotation, and it's called the center for a reason. It's got to be somewhere here in the center where I can actually rotate it on itself. And if we're just brainstorming for some ways, you might think of a couple of different ways, but I think I'm just going to try making an X and see if X marks the spot. So I am finding, if you recall, these are called diagonals of a shape. When you connected the opposite corners, the opposite non-consecutive vertices, I believe was the term we used in Math 2. And if I draw my diagonals, they do intersect, and it is a point fairly close to the middle. And then if we rotate the shape around this point, we find that this parallelogram has a 180-degree rotational symmetry. So 180 degrees around this point, and A lands on C, B lands on D, and D lands on B, and C lands on A, and we still have a parallelogram. So the easiest way to find that point of rotational symmetry, the center of rotation, is to draw the diagonals of the parallelogram, and the point where they intersect is the center. Now, if it is the center of rotation, that tells us a couple of things. If it's 180 degrees, you'll notice that means that side BC lands right on top of side AD, which means that they're congruent, and we already knew that. Parallelograms, opposite sides should be congruent. When we originally learned the shape years ago, that was something that we figured out. But now we actually have the symmetry to back it up. Same thing for CD and BA. When this goes around 180 degrees, it's going to land right on top of this. It also makes these angles be congruent because they land right on top of each other. And these two angles would have to be congruent because they land right on top of each other. It also means some interesting things about these diagonals. If I'm going to rotate 180 degrees around this point, it means this little segment is going to land right on top of this little segment, and vice versa. This segment is going to land right on top of this segment. And that means that this point where they intersect must be the midpoint of those diagonals. So it actually means that these two diagonals have to bisect one another, which is very interesting as well. We know because it is a parallelogram, it's got it in the name, the opposite sides are parallel. So we also know a lot of things about the angles. These two angles would be same side interior angles, which means that they have to be supplementary. They have to add up to equal 180 degrees. And these two angles have to add up and equal 180 degrees. So the whole parallelogram must have 360 degrees. We also know these two have to be supplementary because they're same side interior. So we get a lot of other details about the parallelogram other than just its opposite sides are parallel and its opposite sides are congruent. So let's see if we can maybe make a list of all of these properties. So properties of parallelograms. We know that their opposite sides are congruent. We know their opposite angles are congruent. We figured out that their diagonals bisect each other. That means we get two pairs of congruent segments there in the middle in the diagonals. The consecutive angles are supplementary. They have to add up to equal 180 degrees. We know it has a 180 degree rotational symmetry. And we know that the point of symmetry, the point of rotation, the center of rotation, is where those diagonals intersect each other. So that midpoint of the diagonals. Now this is a lot of information to get from a single word, and that's the change in how you think about vocabulary words when it comes to geometry. You want to make sure that you don't just think of vocabulary as something I have to memorize a definition for, but anytime you see in directions, in a question, and in a problem, parallelogram, that word comes attached with all of this information. Just that one word. When I hear parallelogram, I have to know all of this information. Not that I have to write a sentence definition for it, but this is all the stuff that I now know just because I was given that word. What would be interesting is how much of this information do I actually need to prove that a shape is a parallelogram? Everything we've done so far, it's been one of our given pieces of information. So what would I actually have to know? What would be enough to prove that a shape is a parallelogram? Remember when we did triangles, when we had congruent triangles, or when we did that, it required certain amounts of information to help us to prove that those two shapes were congruent or that they were the same. So how much information is actually needed to prove that a shape is a parallelogram? So let's take a look and see. So proving that a quadrilateral is a parallelogram. If we can prove that the opposite sides are parallel. That is the definition of a parallelogram. So if I can show that the two pairs of opposite sides are in fact parallel to one another, that meets the requirements to be a parallelogram. Sometimes though, we don't know anything about the sides being parallel, and we still want to be able to show that something is a parallelogram. So we can opt to show that the two pairs of opposite sides are congruent. If the opposite sides are congruent, the only way that can happen is if it's a parallelogram. So if those are congruent, then it has to be a parallelogram. It's the only shape with that characteristic. So if two pairs of opposite sides are congruent, it is also a parallelogram. If one pair of opposite sides is parallel and congruent, so maybe we don't know anything about one of the pairs of sides. They're just kind of there and we just don't have any information about them. But if we can prove that one pair of sides is the same length and we know they're parallel, that's enough to prove that the other pair is as well. So we know that it is a parallelogram. If two pairs of opposite angles are congruent, so perhaps we can't show that the opposite sides are congruent, but we can show that the opposite angles are congruent, then we know it is a parallelogram. And if we can prove that one angle is supplementary to both of its consecutive angles. We talked about how we know those same side interior angles have to be supplementary. If I can prove that one corner is supplementary to both of its adjacent corners, then I know that the whole thing has to be a parallelogram because I have all parallel lines. And if we can show that the diagonals do in fact bisect each other. So if we can prove that that point where they intersect is actually the midpoint of both of those segments, then we can prove that the quadrilateral is a parallelogram.